Okay, this section, we have an alternative method for approximating. And this time, this one uses parabolas instead of trapezoids. So there's a couple of technical requirements that have to be met. First one, taken care of by the author. And he has developed a way to integrate a parabola, given a parabola p of x. He's come up with this general formula here. V minus a over 6, and so forth. So that's developed in the text. I'm not going to dwell on that. But suffice it to say, we need 3 points for each parabola. That means we need 2 subintervals to get that. So we'll be using the endpoints of each subinterval. And that means we need an even number of subintervals. N must be even to use Simpson's rule, this parabola technique. It's going to be called Simpson's rule. So the rest of this here, I'm not going to go into the details of it, but you can see how using that formula that the author came up with, we can get the area under each parabola that's created, which is in a double subinterval. And then using several of those, we can generalize in here. And I've done it for the first few. I did the first one here, and the second one here, third one here, and 1, 2, 3. And the idea is that notice there's a pattern in the coefficients. You're doubling these, you're doubling these, you're doubling. So you can generalize and come up with this. And of course, the sum approaches the integral as n goes to infinity. We're not proving that, but we're gonna go with it. We're gonna use it as a fact. That sum approaches the function as n approaches infinity, the area under the function. So here's Simpson's rule, and pay attention to the pattern in the coefficients. It helps you remember it while you're writing it down and using it. It's b minus a over 3n instead of a 2n. And notice the alternation of the coordinate of the coefficients 4, 2, 4, 2, 4, 2, and then 1 on the end. So let's go ahead and use it to do the same integral we just did with n equal 4, and we'll approximate the 4 decimal places as we go. Okay, so we'll chop it off at 4, wherever we get. All right, so we need this. This will be approximately the b minus a over 3n. And then we'll have f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus f of x sub 4. Okay, so that is using our formula directly. All I did was use it here. I've got the 1, 4, 2, 1, 4, 2, 1, 4, 2, and then you ended with a, see, we end with a 1, 4, 2, 4, 2, 4, 2, 4, 2, finally 4, 4, 2, 4, and then 1 at the end. So that's how we got it. You just alternate them until you reach the last one. Okay, so let's go ahead and put in our numbers then. We have, this will be a 1 over 3 times 4 is 12. And then we'll have 0 squared over 2 plus 1 plus 4 times 1/4 squared over 2 plus 1 plus 2 times 1/2 squared over 2 plus 1 plus 4 times 3/4 squared over 2 plus 1 and plus 1 squared over 2 plus 1 is my last term. All right, so we get 1/12. Let's see, that's a 0, that's a 1, and that's a 1 on the end, so we're going to get a 2. Taking care of this and this and this. Okay, and then we're going to have, let's see, I'll get that thickness back down. Okay, let's see, in here, this will be 4 times that, so we'll have a 2 times this 1/16 plus a 4, expanding here. The next one, we'll have a 1/4 plus a 2. The next one will have a 2 times 9/16 plus a 4. Okay, and don't forget that half in there. Sorry about that. It'd be half. We didn't get the half yet. Okay, so plus 1/2. All right, 1/12. Just arithmetic now. 2, 2. Okay, let's go this 2, 6, 8, 12. Okay, this is an 1/8 here. This is a 1/4. And this is 9/8 here. And this is a half over here. Okay, so that's everything. 1/12. Let's see. This will be 12 plus, let's see, we got 10/8, which is, let's see, yeah, 10/8, which is 5 over 4, 10/8. That's this and this. And then we have half, and that's 3/4. So that's 1/12 of, let's see, we'll make this 12 and 8 over 4 is 2, so it's a 14. So this should be 7 over 6. Okay, now, since round that to 4 decimal places, well, okay, so 1.1667. Okay, now, thing is, what you notice, so we did this problem in the last sample we did, and we came up with an exact answer of 7 over 6. This one actually gave us an exact answer. And well, that seems appropriate since this function is a parabola itself. So when you're taking your points, x1, x2, x3, and so forth, to form the approximate curve, you're taking points off of the parabola to approximate a parabola. Well, it only takes 3 points to establish a parabola. So we're getting an exact match with no error at all for our parabolas to approximate the curves. So in each double subinterval. So it stands to reason we get an exact answer.